US Physics Olympiad, year 2013, USAPHO Semifinal Exam. This exam consists of 6 problems, 4 problems A in the first day and 2 problems B section in the second day. For each day they were given 60 minutes. Problem A1. The flow of heat through a material can be described via the thermal conductivity K. If the two faces of a slab of material with the thermal conductivity K, area A, and the thickness D are held at a temperature differing by delta T, the thermal power P transferred through the slab is P equal Ka delta T over D. The heat exchanger is a device which transfers heat between a hot fluid and a cold fluid. They are common in industrial applications such as power plants and heating systems. The heat exchanger shown below consists of 2 rectangular tubes of length L, width W, and height H. The tubes are separated by a metal wall of thickness D and thermal conductivity K. Originally, hot fluid flows through the lower tube and speed V from right to left, and originally cold fluid flows through the upper tube in the opposite direction, left to right, at the same speed. The heat capacity per unit volume of both fluids is C. The hot fluid enters the heat exchanger at a higher temperature than the cold fluid. The difference between the temperatures of the entering fluids is delta Ti. When the fluids exit the heat exchanger, the difference has been reduced to delta Tf. It is possible for the exiting originally cold fluid to have a higher temperature than the exiting originally hot fluid, in which case delta Tf less than 0. Assume that the temperature in each pipe depends only on the lengthwise position, and consider transfer of heat only due to conduction to the metal and due to the bulk movement of fluid. Under the assumptions in this problem, while the temperature of each fluid varies along the length of exchanger, the temperature difference across the wall is the same everywhere. You need not prove this. Find delta Tf in terms of the other given parameters. Solution. Let's formulate the main idea how to solve this problem. We have 2 processes for heat transfers. One process is heat flows from hot liquid to cold liquid, and the other process is hot liquid is coming from one end, and during this motion we are getting hot liquid and we are losing cooler liquid. So we can count the rate how do we lose this heat. Let's convert it to equations. Because we suppose that temperature difference delta T is a constant along this pipe, we can write this equation for heat transfers for time delta T. That's a coefficient of conductivity multiplied by area, which is WL, divided by distance between layers, and multiplied by delta T, the temperature difference, and multiplied by time delta T. This is from one hand. From other hand, we have a hot fluid which is going from right end and this fluid is going cooler from left hand. And if we know what is temperature difference, we can count what was the heat transferred from this liquid, which is equal to this dq. In the same time, volume delta V of red fluid coming from a hot end, and this delta V equals this expression WH V delta T, and the same volume leaving this left end with a lower temperature. Suppose the temperature difference is delta TR. It means that a red liquid getting heat dq equal this expression, and this dq must be equal to this dq, which is heat transfers for the same time delta T. Now suppose that a red liquid enters this pipe with the temperature TR, and the blue liquid enters this pipe with the temperature TB. It means that a red liquid leaves this pipe with temperature TB plus delta T, where delta T is a common temperature difference between red and blue liquids. So it means that overall temperature difference for a red liquid equal TR minus this expression, and the TR minus TB. That's our initial temperature difference between red liquid, which is going inside, and blue liquid, which is going inside. Now we can insert this TR to this expression for dq and equalize them. So from this equation we can find what is delta T, which is delta Ti over 1 plus alpha, where alpha is this coefficient. And now, because a red liquid exits with the temperature Tb plus delta T, and blue liquid exits with the temperature Tr minus delta T, we can count what is the total temperature difference for exiting liquids. So we have delta T final equal this 1 minus this one. So we have this expression, which is negative delta Ti plus 2 delta T, where delta T we already counted. So finally we got this answer where alpha is this coefficient. And we see that for very long pipe, where L is very big, this coefficient is small, and total temperature difference could be negative. For alpha going to infinity, for very long pipe, we can get a reverse result, which is interesting.